Camera. Okay. This is Irfan.
Group 16, right?
Sir, we are from Group 16. Sir, this is me. Sir, this is me. We are from Group 16 and yet we are still do the demonstration here.
Yeah, this is part 1. I just explain from here to the table.
Okay.
So to get LED 1, you have the combination of PDDR and PDOR. So to get 1, PDDR must be 101 and PDOR must be 001. 101 in hexadecimal, right, is 5 and 001 is 1 in hexadecimal. So 5 and 1 combined will get LED 1. LED 2 you need to combine 5 and 4. PDDR 5, PDOR 4. LED 3 you have to combine 3 and 2. So for PDDR 3, PDOR 2. For LED 4 you need to combine 3 and 1. For 5 you need to combine 6 and 4. And then for 6 you need to combine 6 and 2. As you can see here, LED 1, 2, 3, 4, 5, 6.
So this part is the array, okay, which is the 0, 0, 1, 0x2, 0x3, 4, 5, 6. I do it here as Excel because it makes me easier to do the codes. For example, for like I want to light up for LED 1. Okay, for LED 1 you need a combination of 5, 1.
5
we
and 1.
explained before
5 and
1, which is PDDR 5.
PDOR
1. For this case, according to the data sheets, for PDDR, for PDOR, for these operations, 1 is logic high, for 0 is logic low. So in these cases, high and low is actually we can set at PDOR.
Okay.
So likewise, I see PDDR 5, which is in hexadecimal 0x5. While PDOR 1, which is in 0x1. Okay, so this function is how I get the input from the switch. Okay, for in hexadecimal 1, value 1. Which I do everything in hexadecimal because it's easier for me to code for this part, which is the set LED. And after that I call this function set LED and set LED. I get the input from this function, which is integer new. I name this integer new because I want this function to read the new input every time I key in the new input, which I will demonstrate and explain in later on. Okay, now I explain. Now my group member Nazim will demo in hardware. This is my explanation in coding, and now I want to demonstrate in hardware.
Okay, so for the switch
001, which is at first LED 1 is 001. Okay, come 001.
So LED 1 is 0, 0, 1. So this is LED 1.
Okay.
So for LED 2 is 0, 1, 0. So 0, 1, 0 is LED number 2.
Okay.
So for LED number 3 is 0, 1, 1. See it change.
Okay.
Okay. Now for LED number 4 is 1, 0, 0. So 1, 0, 0.
Okay.
LED number 4.
Okay.
LED 5 is 1, 0, 1. And then the last one is 1, 1, 0. Okay.
This
is the 6th, the last one.
So that's all for
Part 1.
Part 1.
The demonstration. Okay.
Hi guys. For my part, I will explain on the platform part for the Charlie plexing, but we call the set LED from the assembly part.
Okay.
In the C function, in the C coding, we only add this part. extend void set LED, which we will call from the here assembly function. In the C, the value of when the switch is 1, we will set the value 1 directly, and the switch is 2 in hexa, we will set the value 2 and 3, 4, 5, 6, so on, which will then be called in the main function set LED here. And this one, when we call, we'll get from the value, we'll get the operating value from the assembly. Okay, in the assembly, firstly we initialize the GPIOC, which is the value of 0x400FFO80. This value
teacher store R1 to R2.
okay, and next is the PDOR offset, which is 0x00, and the PDDR offset is 0x14. This value can be get from the datasheet here. As you can see, the value of GPIOC, which is 400FFO80, and the PDOR offset, which is 0, and for the PDDR is 14.
Okay.
Okay, back to the coding.
Which are edit video.
When the value getting from the C, which will then be inside the register of R0. If the value is 0, it will branch equal and go to the loop 0, which representing the LED 0. But LED 0 for this coding will show that it will, all the LED will not light up. Okay, firstly we load GPIOC inside R0, and then we set 1111 into R1, and then we store the value of R0 PDDR offset and store it into R1. When by this line, it indicates that we are making GPIOC PDDR F11 equals to 0xF, which is 1111, and then we move value of 0 into R1, and then we store the PDOR into R0 and store into R1. And here it shows that our GPIOC PDOR is 0. So basically this coding is indicate that all LED will be light off. Okay, and move back to the here. If the value we obtain from C is 1, if the value we obtain from C is 1, it will branch equal to loop 1, which representing LED 1.
Okay.
As before, firstly we load GPIOC within R0, and then we move 5 into R1, and then we store the PDDR into R1, which makes this line equaling GPIOC PDDR equals to 0x5, and then we move a value of 1 into R1, and then we take back the R0 PDDR and store into the R1. This line will make it GPIOC PDOR equaling 0x1.
Okay.
This can be shown here of why we use the value. The PDDR, we use a value of 101, which in hexa is 5.
Okay.
And for the PDOR, we use a value of 001, which is 1. So it correlates with this value of hexa 05 and 01.
Okay.
Okay. And then
Same thing goes
with the LED 2,
to the
LED 3, LED 4, and LED 5.
6.
LED 6.
Okay.
At the end of this, after we obtain the value of GPIOC and PDOR of each LED, we'll go to the next line of coding, which is branch N. This branch N will then go to here, and BXLR will return the value back to the C.
C coding.
Okay, C coding.
Okay.
For demonstration,
Same as.
is mostly the same as the part 1. Okay, for 001 it will be like LED 1, and then 010 is LED 2, 011 LED 3, and then 110 is LED 4, 100 is LED 4,
Okay.
101 LED 5, and 110 is LED 6. Okay, so that's all for my part. Thank you.
Okay, so now I'm left to present our part 3, which is about part 2B, which is about 1 second delay. And the part 3 is about the combination of 1 second delay and the part 2 which previously presented by Ifan.
Okay. The code is it?
This is the concept, which is very simple. This is just show the LED in teleplexing with a delay.
Okay.
Okay, now for my part, for this part 3, I have the assembly for assembly. This is the assembly and the LED. The LED for this LED assembly in assembly language, which is previously exactly the same, which is previously explained by Ifan, which is by Ifan. And my part, I just add the delay function in assembly. So how I get this value? Okay, for this value, I actually get, I not to say exactly 1 second, approximately 1 second, around 1 second plus.
Okay.
And this is how I get the value. Okay, this. Okay, for as I know, for these microcontrollers, they use the clock. They use 48 megahertz.
Okay.
Okay. So I divide it, you will get this period, and for 1 cycle, the total cycle you needed is 1 over. You still get the, in total you still get the 48 mega cycles. So to count the every single line, to count the number of cycles for this assembly, which is this one. For this coding, I will add some comment and explanation for how I get the calculation for this value and this value. Okay. Later on when I do the submissions. Okay. Now without the comments. For this one is 1 cycle. The branch is 1 cycle. For this one is 1 cycle, and for this one is
1 cycle.
1 cycle. So this is how I get this 1 cycle, and 1 cycle to find the x. X is the R3. That's how I get this value in Hexal it is. But for this value, according to the theory, is supposing to get 1 second. Theoretically. But in the practical way, it shows 3 seconds plus. So in order to get the exact 1 second, I divide by 3 and I get this. After I divide by 3 seconds, I get this value, which is 007A 11FA. Just in this.
Highlight. Oh, okay.
007A 11FA, which is how I did for this thing 16E35FE get 3, approximately 007A 11FA in hexadecimal.
Okay.
So that's how I get the 1 second delay. This is the demonstration. Okay.
Approximately 1 second.
1,000, 2,000, 3,000, 4,000, 5,000 and 6,000, 1,000, 2,000 and so on. You see, I learned this how to count approximately 10 seconds from YouTube. That's how I demo the lab 3 with 1 second delay. That's all for us from group
16.
16. That's all.